You know that phone in your pocket or the supercomputers that predict our weather? There's a hidden engine making all of that possible, and it's called parallel computing. It's the reason our digital world is so ridiculously fast and powerful. So how does this whole thing work? Well, let's dive in and figure it out.
Okay, so what do two cooks in a kitchen and a massive supercomputer have in common? I know, it sounds like the setup to a really nerdy joke, right? But the answer, well, the answer is the key to understanding one of the most powerful ideas in all of modern tech.
All right, first up, one cook versus two. Yeah, we're going to start with a super simple story about making a salad, but trust me, it's going to help us wrap our heads around the huge difference between sequential and parallel computing.
Okay, so check this out. On the left, you've got sequential computing. Just think of it as one cook, all alone, making a salad. They have to do every single thing one step at a time, right? First, wash the lettuce, then chop the tomatoes, then mix the dressing. It's one task right after the other. But now, look at the right side. This is parallel computing. Now we've got two cooks, so one person can be washing the lettuce at the exact same time the other one is chopping the tomatoes. See? They're working together in parallel.
And the result? Well, it's pretty obvious, isn't it? Our single cook, working alone, takes 3 minutes. But our two cooks, because they can split up the work, get it done in just 2. And that right there is the whole secret sauce of parallel computing. You use multiple processors, or cooks, to get a big job done way, way faster.
So Section 2 is all about the need for speed. I mean, getting your salad a minute faster is nice and all, but why is this so unbelievably critical in the world of technology? Let's get into the benefits and, of course, the challenges of going parallel.
Oh man, the advantages are just massive. We're talking about solving problems so much faster. And not just that, we can tackle tasks that are just impossible for a single processor to even think about handling. Things like simulating incredibly complex climate models or crunching mountains of financial data. The time you save? It almost always pays for the extra hardware, and then some.
But, and this is a big but, it's not as simple as just throwing more cooks or processors at every single problem. You know, managing all of them gets really complicated. You have to write special programs that can coordinate all these different workers. And sometimes, one processor literally has to sit around and wait for another one to finish its job before it can even start. So here's the key takeaway. Doubling your processors doesn't always mean you cut the time in half. Some parts of the job just can't be split up, period.
Okay, buckle up for Section 3, 4 parallel blueprints. Now we're going to get a little more technical and talk about the architecture. There's this classic way to classify how these parallel systems are built, and it's called Flynn's taxonomy. Basically, it gives us 4 fundamental blueprints.
Which brings us to the big question, right? If you've got thousands, maybe even millions of processors, how in the world do you get them all to work together without tripping over each other? Well, it turns out there are 4 main ways to do it.
First up, you've got SISD. That stands for Single Instruction, Single Data. Honestly, this is just our baseline single cook model. It's your standard, everyday, non-parallel computer. One stream of instructions, one stream of data. Nice and simple.
Next, we have SIMD, or Single Instruction, Multiple Data. Now, this is where things get interesting. Imagine one instruction is being executed on tons of different pieces of data all at once. The perfect example is editing a photo, right? You have a single instruction like increase brightness by 10%, and it gets applied to millions of individual pixels, all that multiple data at the exact same time. This is precisely what graphics processing units, or GPUs, are absolute masters at.
Then there's MISD, Multiple Instruction, Single Data. This is where you'd have different instructions all working on the same single stream of data. It's kind of weird, and to be honest, it's more of a theoretical thing. You almost never see it used in the real world because very few problems actually fit this model.
And that brings us to the last one, MIMD, Multiple Instruction, Multiple Data. And folks, this is the king. This is the big one. Here, every processor can be running a different instruction on different data. It's like a huge kitchen full of expert chefs, all working on different parts of a giant banquet. This is by far the most flexible and powerful approach, and you'll find it in pretty much every modern multi-core device, from your laptop to the world's biggest supercomputer.
In this many cooks approach, this MIMD style often follows a really common workflow. You can think of it like having a head chef who acts as a manager processor. That manager breaks down the big problem and hands out smaller tasks to all the worker processors. The workers then go off and do their own thing, and once they're done, they report their results back to the manager, who puts it all together for the final answer. All right, on to Section 4, a tale of 2 memories. Look,
Having a bunch of processors is great, but how they share information, how they access their memory is just as crucial. If it takes too long to get the data you need, you can create a massive bottleneck that just erases all the speed you gained.
And there are really two main ways to handle this. On one hand, you have shared memory. I want you to picture this as one big communal pantry that all the cooks can get into. Any cook can grab any ingredient anytime. On the other hand, you have distributed memory. This is more like giving each cook their own personal mini-fridge. If one cook needs something from another cook's fridge, they have to stop what they're doing and specifically ask for it.
So that shared memory model, the big communal pantry, is way easier for programmers to work with. I mean, everyone sees the same data, so sharing is super simple. But just imagine 50 cooks all trying to squeeze into one tiny pantry at the same time. You'd have a total traffic jam, right? That's the problem. This model can become a huge bottleneck, and it just doesn't scale very well when you have a lot of processors. Now, the huge advantage of distributed memory, all those personal fridges, is that it completely solves the traffic problem. It's incredibly scalable. You can just keep adding more and more. The downside, it is so much harder to program. The cooks have to constantly communicate with each other to pass ingredients back and forth, and the programmer has to write all the code to manage that complex dance.
Okay, last section. The world runs in parallel. We've talked about the what and the how, but now let's really nail down why any of this matters to you. How does this kind of abstract concept actually power your everyday life?
Think about this. Every single time you use a search engine, you are tapping into parallel computing on a scale that is just mind-blowing. These systems use these enormous distributed networks of computers to process millions of searches every single second. There is no way at all, a single sequential computer could ever handle that kind of load.
So, what's the bottom line here? Let's wrap it up. Parallel computing gives us this incredible speed to solve problems that would otherwise be completely out of reach. But it's not a magic wand. You have to design it really carefully to manage all that complexity. At the end of the day, though, it is the fundamental engine that makes our modern, data-hungry world go round.
And we're just getting started. We are constantly pushing the limits, always demanding more and more from our technology. You know, from artificial intelligence to huge scientific breakthroughs, the need for raw computing power is just exploding. Parallel computing got us to where we are today. But what's next? What new architecture, what new crazy idea is going to fuel the next great leap forward?